Motion of center of mass. Equipped with the definition of the center of mass, we are now in a position to discuss its physical importance for a system of n particles. We may rewrite equation 7.4d as mr equals summation mi which equals m1r1 plus m2r2 plus till mn_rn. Differentiating the two sides of the equation with respect to the time, we get m into dr by dt equals m1 into dr by dt plus m2 into dr by dt till mn into drn by dt, or m into v equals m1 v1 plus m2 v2 till mn vn, where v1 which equals dr1 by dt is the velocity of the first particle, v2 which equals dr2 by dt is the velocity of the second particle, etc. And v equals dr by dt is the velocity of the center of mass. Note that we assume the mass m1, m2, etc. do not change in time. We have therefore treated them as constants in differentiating the equation with respect to time. Differentiating equation 7.8 with respect to time, we obtain m dv by dt equals m1 into dv1 by dt plus m2 into dv2 by dt till mn into dvn by dt, or m into a equals m1a1 plus m2a2 till mnan, where a1 equals dv1 by dt is the acceleration of the first particle, a2 which equals dv2 by dt is the acceleration of the second particle, etc. and a equals dv by dt is the acceleration of the center of mass of the system of particles. Now, from Newton's second law, the force acting on the first particle is given by F1 equals m1a1. The force acting on the second particle is given by F2 equals m2a2, and so on. Equation 7.9 may be written as ma equals F1 plus F2 plus till Fn. Thus, the total mass of a system of particle times the acceleration of its center of mass is the vector sum of all the forces acting on the system of particles. Note, when we talk of the force F1 on the first particle, it is not a single force, but the vector sum of all the forces on the first particle. Likewise for the second particle, etc. Among these forces on each particle, there will be external forces exerted by bodies outside the system and also internal forces exerted by the particles on one another. We know from Newton's third law that these internal forces occur in equal and opposite pairs, and in the sum of forces of equation 7.10, their contribution is 0. Only the external forces contribute to the equation. We can then rewrite equation 7.10 as ma equals F external, where F external represents the sum of all external forces acting on the particles of the system. Equation 7.11 states that the center of mass of the system of particles moves as if all the mass of the system was concentrated at the center of mass and all the external forces were applied to at that point. Notice, to determine the motion of the center of mass, no knowledge of internal forces of the system of particles is required. For this purpose, we need to know only the external forces. To obtain equation 7.11, we did not need to specify the nature of system of particles. The system may be collection of particles in which there may be all kinds of internal motions, or it may be rigid body which has either pure translational motion or a combination of translational and rotational motion. Whatever is a system and the motion of its individual particles, the center of mass moves according to equation 7.11. Instead of treating extended bodies as a single particle, as we have done in earlier chapters, we can now treat them as a system of particles. We can obtain the translational component of their motion, that is, the motion of the center of mass of the system, by taking the mass of the whole system to be concentrated at the center of mass and all the external forces on the system to be acting at the center of mass. This is a procedure that we followed earlier in analyzing forces on bodies and solving problems without explicitly outlining and justifying the procedure. We now realize that in earlier studies we assumed without saying so that rotational motion and or internal motion of the particles were either absent or negligible. We no longer needed to do this. we have not only found the justification of the procedure we followed earlier, but we also have found how to describe and separate the translational motion of 1. A rigid body which may be rotating as well, or 2. A system of particles with all kinds of internal motion. Figure 7.12. The center of mass of the fragments of the projectile continues along the same parabolic path which it would have followed if there were no explosion. Figure 7.12 is a good illustration of equation 7.11. A projectile following the usual parabolic trajectory explodes into fragments midway in the air. The forces leading to the explosion are internal forces. They contribute nothing to the motion of the center of mass. The total external force, namely the force of gravity acting on the body, is the same before and after the explosion. The center of mass under the influence of the external force continues, therefore, along the same parabolic trajectory as it would have followed if there were no explosion.